Hi guys! In this video, I will discuss another technique of integration called integration by partial fractions. This technique is helpful if your integrand is a rational expression. That is, if the integrand is of the form polynomial divided by polynomial. So let's get started. Let us consider the sum of these two rational expressions, 2 over x minus 2 plus 3 over x plus 1. If we combine these two rational expressions by adding them into a single rational expression, then we will end up with 5x minus 4 over x squared minus x minus 2. Now, if we want to integrate this expression here, so we want the integral of 5x minus 4 over x squared minus x minus 2 dx. Since we know that this expression here is equal to this sum in here, then we can rewrite this integral here, to this integral. So now we have the integral of 2 over x minus 2 plus 3 over x plus 1 dx. Using simple substitution and integrating it, we will end up with the following expression. 2 ln absolute value of x minus 2 plus 3 ln absolute value of x plus 1 plus c. So this is an illustration of how integration by partial fractions is done. This expression here on the left-hand side is called a partial fraction decomposition of this expression here on the right. Hence the name partial integration by partial fractions. So, how do we do this? First, let us define some things. Let f and g be polynomials. If the degree of f is less than the degree of g, we say that the rational function is proper. So if you remember, this is consistent with the definition of proper fractions. If the numerator of a fraction is less than the denominator of the fraction, we call it a proper fraction. So in terms of functions, particularly rational functions, we want the degree of the numerator to be less than the degree of the denominator. Of course, otherwise, if the degree of the numerator is greater than or equal to the degree of the denominator, then we call the function improper. Okay? Now, if we have an improper rational expression, then we can divide f by g using possibly long division, or if you know synthetic division, you can use that. But if we actually divide f by g, then f over g can be written into another expression. Let's write it of the form q of x plus r of x over g of x, where the degree of r of x is less than or equal to the degree of g of x, or possibly r of x is equal to 0, meaning we only have q of x after the division. Okay? So again, if your rational expression is improper, then you can do long division or synthetic division in order to write it in this form. Q of x plus r of x over g of x, where the degree of r of x is less than the degree of g of x, or r of x is equal to 0. It is possible that r of x is equal to 0. So if you remember, this q of x is called the quotient. The r of x here is called the remainder. Okay? So, here, the q of x, since we are talking about rational function or rational expression, q of x here will be a polynomial. Okay? So if we integrate this expression here with respect to x, then we are just integrating this sum here with respect to x. And since this is just a polynomial, we can integrate this easily. So our problem now is to integrate this part here. Now, the point that I want to make here is that if we got an improper expression, improper rational expression, we do this long division in order to write it this way. And we always end up with a proper rational expression. Or maybe this part here is equal to 0. Okay? But the point here is, since we can easily find the integral of a polynomial, it is enough to learn the technique integration by partial fractions if our rational expression in the integrand is a proper rational expression. If it is improper, we do the long division. If it is proper, then we just proceed with our technique. So, for example, here we got integral of x cubed plus x plus 1 over x plus 1 dx. So notice the degree in the numerator is 3, the degree on the denominator is 1. So this expression here as a whole is an improper rational expression. If we do the long division, we will end up with the following. So in here, let us actually divide it. X cubed plus x plus 1 divided by x plus 1. I hope you still remember your long division. So this will be x squared. We have here x cubed plus x squared divided, subtract this. We will have negative x squared plus x plus 1. And then we will have here minus x squared minus x here. And then let me just move this one here to this side here to get some space. And then we have here, we subtract, and then we will have here 2x plus 1, and then here you will have plus 2. We have here 2x plus 2, then we subtract. Our final remainder here will be minus 1. So what does this mean? This means that this integral here, or this expression here, can be written as the integral of x squared minus x plus 2 minus 1 over x plus 1 dx. So from this expression, after doing long division, we get this expression. So if we want to integrate this one, we just need to integrate this expression, which is much easier to do compared to this integral here. Therefore, integrating, we will have x cubed over 3 minus x squared over 2 plus 2x minus, in here you can do simple substitution, but a lot of times if the denominator here is linear, then we can skip that substitution technique and just simply write ln of that denominator, or absolute value of that denominator. And then we have the plus c. So this will be the final answer for this integral here. So again, if your integrand, for example, this one is an improper rational expression, you do your long division in order to get this expression on the right-hand side. Q of x will always be a polynomial. This one will be a proper rational expression or equal to 0. Right? So, it is enough to learn the technique if our integrand is a proper rational expression. Now, some remarks that I just want to make before I proceed. Here, if capital F of x is an antiderivative of small f of x, then if we want to integrate f of ax plus b dx, this will be equal to capital F of ax plus b divided by a plus some arbitrary constant c. Particularly, if you have the integral of 1 over ax plus b dx, we can skip the u substitution and just simply write ln absolute value of ax plus b over a plus the arbitrary constant c. Okay, so we can skip that part. But in general, this expression here is true. This identity here is true. Again, if capital F of x is an antiderivative of small f of x. And this can be done if you only have linear expression inside. Okay? If it is quadratic inside or whatever, you might need more. But in this case, we only want linear. So that just a simple remark. So we can always skip u substitution just like what we did in this case here. We skip the u substitution and simply write ln absolute value of x plus 1. Take note, the coefficient of x here is 1, so this one is actually over 1, but that's over 1. So we can remove that one. Okay? Now, the integration by partial fractions involve several cases. So for the remaining time, I will do maybe few cases, at least 2, that's my target, before I finish the video, and the rest will be discussed during our next session. Now, first case. Suppose q of x can be written as a product of distinct linear factors. Meaning, suppose your q of x here is equal to a1x plus b1, times a2x plus b2 times a3x plus b3 plus etc. until times a, k, x plus bk. Again, distinct linear factors. So each of the factor that you see here is different from the other factors. So if this is the case, then p of x over q of x, again, in here we want this to be a proper fraction, meaning the degree of p is less than the degree of q. The degree of p is less than the degree of q. If your q of x can be written as a product of distinct linear factors, then p over q can be written as follows. Capital A1 over A1x plus B1 plus capital A2 over A2x plus B2 plus until capital AK over AKX plus BK. Meaning you can decompose your P of x over Q of x into a sum of fractions with linear denominators. The numerator here, notice there is no variable. In here, there's no variable. The numerators, capital A1, capital A2, until capital AK, they are all constants. They are just numbers, no variable. So, in here, your Q of x must be factored into distinct linear factors. This means that you will need your factoring skills. So if you need to, try to practice your factoring. Try to do some factoring problems. You will need it in this technique. So, example, we want to integrate x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. In here, I have already factored the denominator into x times 2x minus 1 times x plus 2. Okay? So, this case here says that your x squared plus 2x minus 1 divided by 2x cubed plus 3x squared minus 2x, since the factored form of the denominator is this expression, look at the factors x, 2x minus 1, x plus 2. This rational expression here can be written as a 1 over x plus a 2 over 2x minus 1 plus a 3 over x plus 2. So again, if you are able to write this into a product of linear factors, which I have already shown you in this part, then the fraction itself can be written into a sum of fractions with linear denominators. And the denominators, these are just the factors of the original denominator here. Now, the problem here is how do we get A1, A2, and A3. In order to do this, well, what you need to do is to combine this into a single fraction, but with the use of A1, A2, and A3. Meaning, if we do that, of course, you will have your denominator as x times 2x minus 1 times x plus 2. A1, since the denominator of A1 is already x, you will multiply your A1 to the other denominators here. You will have here 2x minus 1, x plus 2, plus, next, for A2, since the denominator of A2 is 2x minus 1, you will have to multiply your A2 with the other denominators here. So x and x plus 2, and similarly, your A3 will be multiplied by x and 2x minus 1 because the denominator of A3 is this expression here. Now, the next thing to do here is one way is to combine, multiply and combine this expression and simplify. And then you will compare coefficients. You want this expression here to be equal to this expression. Meaning, you got your x squared plus 2x minus 1. This must be equal to a times 2x minus 1, x plus 2, plus, sorry, a1 here, then a2, x plus 2, plus a3, x 2x minus 1. So the numerator of the original expression must be equal to the numerator of, the combined form of your partial fraction decomposition. Then you will solve it. You can simplify this and then get the coefficient of your x squared and then compare it to the coefficient of x squared here, which is 1. So the coefficient of x squared here must be equal to 1. The coefficient of x here must be equal to 2. And the constant term of this expression here must be equal to negative 1. In the end, you will be solving a system of equation. That's one way to do it. Another way to do it is by substitution. You need to substitute some numbers on both sides of the equation. So you let x equal something, substitute that something to the left-hand side and to the right-hand side, and you will find the values of A1, A2, and A3. Then choose another number, substitute it on the left-hand side, and on the right-hand side, you will equate that. Then you'll be able to find, actually not find, but write the number in terms of A1, A2, and A3. Then you might need a third number and then substitute it on both sides of the equation and then write A1, A2, and A3 in terms of the other number. I mean, write this number in terms of A1, A2, and A3. Since there are three unknowns here, in a sense, A1, A2, and A3 are unknowns, you will need three equations. If you've done your linear algebra, then you can use your linear algebra techniques, solving systems of equations. Otherwise, well, you will need to recall what you did during your functions class or algebra class. A simpler, to simplify the solution, I suggest you use x, you replace x with values that will make each of the factor equal to 0. That will simplify your solution. For instance, if we let x equal 0 because of this denominator here, okay? If x equals 0, notice that the left-hand side becomes negative 1. The right-hand side is a1 times 0 minus 1 times 0 plus 2. And because there is a factor x here and a factor x here, whatever this one is or this one is, whatever this and this are, since this is equal to 0, this is equal to 0, this expression will disappear. So now we are just left with a1. And observe that we got here negative 1 times positive 2. This will be equal to negative 2a1, which means that a1 equals negative half. Nice choice of value of x. We can do x equals 1 half. Why 1 half? When x equals 1 half, this will be equal to 0. So this will be gone. This also will be equal to 0 when x equals 1 half. So this will be gone. On the other hand, this part here will not be equal to 0 because x equals 1 half. This one becomes 1 half, this one becomes 1 half. 1 half plus 2 is not equal to 0. So only these two expressions will disappear when x equals 1 half. And therefore, we will be able to find a sub 2. So when x equals 1 half, on the left-hand side, we have 1 half squared plus 2 times 1 half minus 1. This will be equal to a sub 2 times 1 half times 1 half plus 2. On the left-hand side, this 2 times 1 half is positive 1 minus 1, this will be 0, which means that on the left-hand side, you will just have 1/4. On the right-hand side, you got here 1 half plus 2. This is 5 halves times 1 half, that's 5/4. So this will be equal to a2 times 5/4, which means that the value of a2 will be equal to 1/5. So a1 equals negative 1 half, a2 equals 1/5. Finally, to solve for the other one, a3, we can let x equals negative 2. So first one, we let x equal 0 because x is a factor. Second one, we let x equals 1/2 because 2x minus 1 is a factor. Third one, we will let x equals -2 because x plus 2 is a factor. So when x equals -2, the left-hand side is -2 squared plus 2 times -2 minus 1. On the right-hand side, when x equals -2, this will be 0. So this will disappear. This will be 0. So this will disappear. And we will be left with 8/3 times -2 times 2 times -2 minus 1. And then this will give us what? This is -2 squared, that's +4. 2 times -2, that's -4. So 4 plus -4, that will be equal to 0. On the left-hand side, we have -1. On the right-hand side, what do we have? We have here 2 times -2, that's -4 minus 1. That's -5. -5 times -2, that's +10. So we will have here a 3 times +10, which means that a3, this is equal to -1/10. So we now have found the values of a1, a2, and a3, which means this part here, the right-hand side, will be equal to -1/2 x plus a2 is 1/5, 1/5 over 2x minus 1, and a3 is -1/10 plus -1/10 x plus 2. So what does this mean? Well, this expression here is equal to this expression, which means that we can now simplify our integrand into the following. So this one equals integral of this expression. And then, of course, we got the dx. So integrating, we will have -1/2 ln absolute value of x plus 1/5 ln absolute value of 2x minus 1 over 2. I'll put minus 1/10 ln absolute value of x plus 2 plus the arbitrary constant c. Right? So that's how we do it when the expression, when the denominator of the rational expression has distinct linear factors. So let me just go back to the previous slide to see all the steps. So this expression can be written in the form a1 over x plus a2 over 2x minus 1 plus a3 over x plus 2. So linear denominators. And then our goal is to find a1, a2, and a3. In order to do that, you combine this into a single fraction this way. And then from there, you proceed with whatever technique you can use from linear algebra or from functions class. One way to do it is to simplify this expression So you will have like coefficient times x squared plus another coefficient times x plus another coefficient, plus a constant in terms of a1, a2, and a3. The coefficients are in terms of a1, a2, and a3. Then you compare those coefficients and constant with the coefficients and constant of the original fraction. Or what you can do, another method, another way is to substitute x with numbers. Since you have three unknowns, a1, a2, and a3, you use three values for x. Then you will be able to write a system of linear equations. If your denominator is factored into distinct linear factors, the best numbers that you can use for your x are the zeros of these factors. In our case, we got x equals 0, x equals 1/2, and x equals -2. And then once you've done that, you will be able to get your a1, a2, and a3. Then substitute them into your expression here. And finally, you have this partial fraction decomposition of your original fraction. Then you proceed with your integral. So that's for distinct linear factor. That's for case number 1. Case number 2. If your q of x can be written as a product of linear factors, but some factors are repeated. Some factors are repeated, meaning some factors are actually ax plus b to the power r for some r. Then each repeated factor, for example, this factor here, ax plus b to the power r, for each power of ax plus b, you will put a numerator. What I'm saying is, you got the factor ax plus b to the power r. In the decomposition, you should see a1 over ax plus b plus a2 over ax plus b squared. Then you will have here a3 over ax plus b cubed plus until to the highest power of ax plus b, which in our case r. So you will put to each power of the repeated factor a constant numerator. In order to understand this, let us consider this expression or this integral. The integral of 4x over x cubed minus x squared minus x plus 1 dx. And again, I have already factored the denominator into this. The factored form is x minus 1 squared. Look at that. There's a power 2 times x plus 1. So x minus 1 is a repeated factor. So how do we use case 2? So again, you want to find a partial fraction decomposition of the original integrand. You have 4x over x cubed minus x squared minus x plus 1. Since we got a repeated factor, x minus 1, let us use a for that x minus 1. You will have a1 over x minus 1 plus a2 over x minus 1 squared. So to each power of x minus 1, we put a numerator, a constant numerator. We have the power 1 for x minus 1, and then the power 2 for your x minus 1. That's for this case. And again, also do not forget the other factor. In this case, I'll be using b for the numerator. B over x plus 1. Okay? So again, this part here corresponds to the factor x minus 1 squared. If it was x minus 1 cubed, then you put another one here, the one that will correspond to the power 3, and so on. So again, our goal is to find the values of these numerators. And in order to do that, we combine them again into a single fraction. The denominator will be x minus 1 squared times x plus 1. That's the actual denominator that you see in here. For the numerator, it's quite tricky in a sense, but if you practice this, if you remember how to combine such expressions, then good. Otherwise, try to recall how to do it. So let me explain this one here. Of course, you will have your a1. The denominator for a1 is x minus 1, but the denominator of the original expression is x minus 1 squared. This has power 1. This is power 2, which means a1 is missing another x minus 1. Furthermore, the denominator is only x minus 1. It is also missing x plus 1. Okay? For a2, we got here a sub 2. The denominator of a sub 2 is x minus 1 squared. Denominator is already x minus 1 squared. So a2 is only missing this expression. So a2 is only multiplied to x plus 1. Finally, for b, its denominator is x plus 1. Its denominator is x plus 1, but the denominator has x minus 1 squared. So b must be multiplied to x minus 1 squared because from here it is missing the x minus 1 squared. Now, just like before, this expression here must be equal to this original rational expression, or that the numerator must be equal to this numerator here. So we write that for x equals a1 times x minus 1, x plus 1, plus a2, x plus 1, plus b times x minus 1 squared. So again, you can expand this and simplify, and then compare coefficients. This expression here will have x squared, but you don't see your x squared here. It means that the coefficient of x squared here must be equal to 0. This one does have a constant term, but the left-hand side does not have a constant term, meaning the constant term of this expression must be equal to 0. The linear term of this expression will be equal to 4 because there's a linear term here. So here, after you expand and simplify, the coefficients of x squared and x and the constant term of this right-hand side will be in terms of a1, a2, and b. Then you will compare it to the coefficient of x squared here, which is equal to 0, the coefficient of the linear term here, which is equal to 4, and the constant term here, which is equal to 0. Now, that's one way. And another way is to substitute the x with numbers. You need 3 values for x to find these numbers. And just like what we did in the previous case, you choose the best numbers, in a sense that you will easily find the values of A1, A2, and B after a simple substitution. I mean, a simple replacement of your x. The best numbers will be the zeros of the denominator, particularly this denominator here. The zeros of the denominator will be x equals 1 and x equals minus 1. So you can use them. For example, x equals 1. When x equals 1, this will be equal to 0. This will not be equal to 0. This will be equal to 0. So when x equals 1, this will disappear, which means that we have here 4 times 1 equals a2 times 1 plus 1. But this one means 4 equals 2a2, which means that a2 is equal to 4 over 2, which is equal to. When x equals minus 1, this one here will be equal to 0. This one here will be equal to 0. But this will not be equal to 0. So when x equals minus 1, this will disappear, and we will be left with this expression. So we will be able to solve b quickly. So we will have here 4 times negative 1 equals b times negative 1 minus 1 squared. So again, when x equals minus 1, this will be 0 because of this. This will be 0 because of this. This means that you will have negative 4 equals negative 1 minus 1, that's negative 2. If we square it, that becomes positive 4. So we will have 4b, which means b equals negative 1. Finally, we need to solve for a1. So notice that there are only 2 zeros for the denominator, so we can only use 2 of them. I mean the 2 zeros. So we will only be able to find 2 values among A1, A2, and A3. In our case, we were able to find A2 and B. Sorry, A1, A2, and B. In our case, we were only able to find the values of A2 and B. So we need to find the value of A1. But we don't have another zero. Well, we can use a different number instead of the zeros. You can actually, from the very beginning here, you can actually use other values of x that are not zeros of the denominator. We are only using the zeros of the denominator because it simplifies our solution. So anyway, to solve for a1, we again let x be equal to another number. Another nice number is when x equals 0. You can use x equals 2, x equals 5, x equals your favorite number, whatever. But I am using x equals 0 because, well, 0 is a very, very nice number. On the left-hand side, 4 times 0, well, that will be equal to 0. On the right-hand side, we will have a1 times 0 minus 1 times 0 plus 1 plus a2, take note of this, a2, but we already have a2 equals 2. So we can use it. a2 is 2 times 0 plus 1 plus b times this expression, but b is already equal to negative 1. So we'll just have negative 1 times 0 minus 1 squared. So notice, the only unknown in this expression is a1. So we can solve for a1. This is just a simple linear equation. Left-hand side is equal to 0. Right-hand side, we have here minus 1 times 1, that's minus 1. So we will have minus a1 plus 2 times 1, that's equal to 2. Here you got negative 1 squared, that's positive 1, times negative 1, that will be negative 1, so minus 1. So solving, we will end up with a1 equals positive 1. So we bring this to the other side, that becomes a1, 2 minus 1, that's positive 1. So now, we got a2, b, and a1. Therefore, this integral here, let me now go to the next page. This integral here becomes integral of a1 is positive 1, and the denominator is x minus 1. So we will have here 1 over x minus 1. And then a2 is positive 2. The denominator is x minus 1 squared. So plus 2 over x minus 1 squared. And b is negative 1. The denominator is x plus 1. So we will have minus over x plus 1 dx. So integrating, the first one is just ln absolute value of x minus 1. For the second one, take note this one here. This is like of the form integral of 1 over x squared dx, or we have the integral of x raised to negative 2 dx. So if we integrate this will be x raised to negative 1 over negative 1 plus arbitrary constant here. So let me just write c sub 1. But remember the remark, instead of x we have x minus 1. So this one, we skip the u substitution. This one will be plus 2 times x minus 1 raised to negative 1 over negative 1. And the coefficient here is positive 1. So technically, we will have to write the times 1 there. But anyway, that's just times 1. Take note that this negative 1 came from this one here, the new exponent after integrating. And then lastly, for this expression, we have minus ln absolute value of x plus 1 plus the arbitrary constancy. So this will be the final answer. Okay? So again, for this case, we have a repeated factor. Say ax plus b is repeated and it has power r. For each power of ax plus b from 1 up to the highest power r, you write a corresponding numerator. In our example, the repeated factor is x minus 1 and it has power 2. So for each power of x minus 1, power 1 and power 2, there is a corresponding numerator. And then we proceed with the solving of A1, A2, and B. Or we proceed with the solving of the numerators. Right? So that's all for this video. In our next meeting, we will discuss the other cases, integration by partial fractions. I have uploaded some exercise sets in our folder, so you can work on them for now to get more examples for these two cases. And during, in one of our next meetings, maybe I will give you some more problems or some more examples with worked out solutions. So thank you for listening and have a great day.